Hey guys, good morning. Hope all are doing good. So, in today's video, let us discuss about the UG topics of semester 5, paper 5, electromagnetism. So, in electromagnetism, paper 5, semester 5, we are having 4 units: electrostatics, electromagnetostatics, electromagnetic induction, and electromagnetic waves. So, in today's video, let us discuss about electrostatics first topic, right? So, the first topic in electrostatics is electric field and intensity of electric field. Intensity of electric field. Correct? So first, let us know what is this electric field. Then let us go for electric field intensity and its mathematical expression. Alright. Now, here, first electric field. So before discussing about electric field, once for 5 minutes, let us go to know what is charge. So as we know that every substance is made of atoms. Such atoms consist of a central heavy positively charged portion called as nucleus. And this nucleus is comprised of protons and neutrons. Right? Now, around this nucleus, electrons revolve in different orbits. Right? Now, here, the proton, we have positive charge, and the electron, we have negative charge, and the neutron is chargeless. Right? Now, this charge of either proton or neutron is 1.6 into 10 to the power of minus 19 coulombs. Now, here, to know about this charge, so number of experiments are done. The first experiment is done by the Greek philosopher Thales. So he rubbed amber with, he took amber and rubbed with wool cloth. When he brought some light weight objects such as the pieces of paper, he observed that it attracted them. Now after that, an English philosopher, Gilbert, he also did the same experiments by rubbing the glass, ebonite, sulfur, etc. And he found in the same property. They attract some light pieces of objects. Right? Now, this property, we call it as the body is electrified. Or we can say that as charge. The body is charged. Okay, the property of attracting the light pieces which I said, then we call that property as the body is electrified or charged. Now if we take the example of a glass rod rubbed with a silk cloth, what happens here? Glass rod, when it is rubbed with silk cloth, right? Now, glass rod becomes positively charged. Silk cloth becomes negatively charged. How it happens? When we rub the glass rod with the silk cloth, glass rod loses electrons. And that lost electron is gained by silk cloth. Okay? So now, by losing the electron, glass rod becomes positively charged. So we call it as the deficiency of electron of substances we term as positive charge. Now here, that lost electrons are accepted by the silk cloth or gained by the silk cloth. So, and it became negatively charged. So now the gaining of electrons by a substance we term as negative charge. So in such a way, the experiments brought about this theory of charge. Alright. Now next, let us take such a positive charge. Right? I took a positive charge. Okay. Now, what I am doing is, I am taking another similar positive charge, Q naught. The similar positive charge, Q naught. This we call it as test charge. Right? Now what I am doing is, I am bringing this unit positive charge towards this positive charge. I am bringing this test charge towards this positive charge. Right? So now, when it is very far away from this positive charge, Q naught will not experience any force. But as I bring this test charge towards this positive charge, now this test charge, as it comes closer towards this positive charge, this test charge experiences a force. Right? This test charge, when I brought this test charge into this region, it starts experiencing such force. Right? It starts experiencing some force. What will be that some force? First, what happens? The charge comes towards the positive charge. Means there will be force of attraction between them. Now, as this charge come closer and closer to this test charge, what happened? Now, force of repulsion starts acting. Force of repulsion starts acting. Right? Means totally this charge is experiencing certain force due to this positive charge Q in this particular region. So now this region surrounded by this positive charge, we call it as electric field. The region or space surrounded by unit positive charge, we call it as electric field. So after entering, means it is having its effect up to certain region. It is having its effect up to this certain region. If any other charge comes into this region only, it experiences certain force. If not, it will be neutral. Alright? If this another charge comes into this region, it experiences certain force. So this region surrounded by this unit positive charge, we call it as electric field. Alright? Now next, let us discuss about intensity of electric field. Right? Intensity of electric field. Now only we discussed, when I bring a test charge towards the positive charge, when I bring the test charge towards the positive charge, and when this test charge enters into the region where plus Q's effect is present, okay, where plus Q's effect is present, then this test charge experiences a force. So that force experienced by the unit positive charge, we call it as electric field intensity. the force experienced by unit positive charge. We call it as electric field intensity, right? Now, the units of these are for force what? Newton. For charge, Coulomb. So, units are Newton per Coulomb. Okay. So, the units are Newton per Coulomb. Okay. So, now next, let us derive the mathematical form of this intensity of electric field. So, for that, let us assume okay. So, let us assume a positive charge Q at point O, right? Now, let us assume that at a certain distance R, a test charge Q is present. Let us assume Q as unit positive charge, right? Unit positive charge. Now, we are bringing this unit positive charge towards this charge capital Q, which is at a distance R from, you assume this point as P, at a distance R from P at O, right? Now, I think you know about Coulomb's law. So here, once let us talk about Coulomb's law. What Coulomb said? Now, he took two unlike charges or like charges, right? Two charges. Now, he separated that two charges with a distance r. So, now, force of attraction or force of repulsion is directly proportional to the magnitude of product of magnitude of two charges, inversely proportional to the square of distance between them. So, F proportional to Q1, Q2 by R square, right? F proportional to Q1, Q2 by R square, or F equal to K, Q1, Q2 by R square, where K we call it as proportionality constant, and that proportionality constant is equal to 1 by 4 by epsilon naught, where epsilon naught we call it as permittivity of the medium, right? So now F is equal to 1 by 4 pi epsilon naught Q1, Q2 by R square, right? Q1, Q2 by R square. Now this is Coulomb's law for electric charges. The force of attraction or repulsion is directly proportional to the product of magnitude of their charges and inversely proportional to the square of distance between them. So, F is equal to 1 by 4 pi epsilon naught Q1, Q2 by R square. Okay. So, now, applying the Coulomb's law here, F is equal to 1 by 4 pi epsilon naught capital Q by R square. Right? Now, next, here, electric field intensity. So, what we defined electric field intensity? We defined electric field intensity as the force acting on unit positive charge or the force experienced by unit positive charge, right? So, now substituting this value here, F is equal to 1 by 4 pi epsilon naught, sorry, E is equal to 1 by 4 pi epsilon naught capital Q small q by R square divided by Q. So, Q, so answer is 1 by 4 pi epsilon naught Q by R square. Alright. So, this is electric field intensity. Okay. 1 by 4 pi epsilon naught Q by R square due to point charge. Electric field intensity due to point charge coming towards this charge Q. Right? This is about electric field intensity due to unit positive charge. That is 1 by 4 by epsilon naught Q by R square. Now in this, hope you understood this topic. Now let us move on the next topic. The next topic is electric flux. The next topic is electric field lines. Then let us go for electric flux. First, electric field lines. Now, what are these field lines? Now here, I said unit positive charge plus Q will have its effect until certain region. So that region or space surrounded by the effect of unit positive charge, we call it as electric field. Okay. So now let us consider such electric field. So I'm just, this circle shows the electric field. Okay. The effect of positive charge. Okay. So now in this electric field, uniform electric field I took. In this electric field, I'm considering a positive charge. First, I kept it at a point O. Then this charge is moving from point O, let us assume that, to A, again A to B, B to C, C to D, in such a way. Now, the charge is moving from one point to another point in electric field. This is nothing but electric field. Electric field has direction as well as magnitude. So this is a vector quantity. It has direction as well as magnitude. So it is a vector quantity. Right? So now it is moving from one place to another place. Now I will trace the path of this charge. Tracing the path means I'm going on joining O to A to B, B to C, C to D. When I trace the path, I will get this path as a straight line or curved lines. So if we trace the path of unit positive charge moving in an electric field, then we will get either straight lines or curved lines. So these imaginary lines drawn along the path of unit positive charge in an electric field, we call it as electric field lines. Okay, so these imaginary lines drawn along the path of unit positive charge in moving in electric field, we call it as electric field lines. Right? And now, the next, so in such a way, electric field lines. Now, I said that electric field is a vector quantity. So now here, we need this electric field is comprised of this electric field lines only. So as we are saying it is a vector quantity, we need the direction as well as magnitude. Okay. So first, let us discuss about the direction of electric field or electric flux lines. Okay. So now, here I said that we draw these lines by joining the each and every point up to which the charge has passed in electric field. Now, at each and every point, I just go on drawing the tangents in such a way. I'm drawing the tangents at each and every point in such a way. Again, I will keep an arrowhead. Right? Now, this arrowhead indicates the direction of field lines. First, I drawn the tangents at each and every point on field line. Then I kept an arrowhead. And this arrowhead indicates the direction of field lines. Now, next, magnitude. So, to find the magnitude, so in such a way, I drawed the flux lines. Okay. So, these are the field lines, or we also call it as electric flux lines. Right? Now, I draw the flux lines or field lines. Now, I'm considering a area, okay, a area perpendicular to this flow of field lines. Okay, I'm considering the area perpendicular to the flow of lines, right? Flow of field lines or flux lines. Now, see, these are the particular flux lines passing through this area normal to the flow of flux lines. So, this number of flux lines, right? The number of flux lines passing through area perpendicular to the direction of flow of lines gives the magnitude of that flux lines, right? So, direction by drawing the tangent at each and every point along the flux lines gives the direction of the flux lines. And the magnitude, if we consider any area. So, now if this is the area, now these are the flux lines. I consider the area perpendicular to the flux lines, right? Now, the number of flux lines flowing through this area perpendicular to the flow of flux lines gives the magnitude of that particular flux lines, right? Now, the next step. Now, what happens? What will be the direction of flux lines? If I take unit positive charge, I took unit positive charge. So, if I take an isolated positive charge, if I take an isolated positive charge, the direction of flux lines starts from the positive charge and ends in infinity. Starts from the positive charge and ends in the infinity. Means flux lines, if we take the isolated positive charge, flux lines are moving away from plus Q, right? Away from the Q. Now next, if I take isolated negative charge, then flux lines from infinity move towards the negative charge. Flux lines from infinity moves towards the negative charge. Means flux lines here are outwards and the flux lines here are inwards. Right? Important point to remember. If we take the positive charge, flux lines flow outwards. If we take the negative charge, flux lines flows inwards. Means from infinity towards the negative charge, inwards. Right? Now, if we take both the same charges, two charges. Now, before we talked about isolated charge, now let us take the same charges. Or first, unlike charges, I will explain. Plus, minus. Flux lines every time flows from positive to negative. Positive to negative, right? Flux lines flows from positive to negative, right? Positive to negative. To negative. Correct? If we take unlike charges. Similarly, if we take like charges, if we take like charges, correct? What happens? A repulsion will be there. So, flux lines. In such a way, the pattern of flux lines, correct? Here also, right? Now here, there will be a point here, right? Here, in between these two, at point N, electric field will be 0. If you place any charge, it remains neutral because electric field is equal to 0. So this is about the field lines or flux lines. Now next, let us go for some properties of these flux lines, right? Properties of flux lines. The first property is, now only what we said, the tangent drawn at each and every point on flux lines indicates the direction of flux lines. Indicates the direction of flux lines. Second point, the flux lines starts from positive charge and ends at negative charge. Starts from positive charge and ends at negative charge. Next, these flux lines, every time they are parallel to each other. Parallel to each other means they never intersect with each other. They never intersect. For example, let us think that actually flux lines will be parallel to each other. Instead, let us think that they are intersecting with each other. If they are intersecting with each other. If they intersect, what happens? We will have two force directions. But is two force directions possible? It is impossible. We will not have two force directions. So only these flux lines never intersect with each other. Now next one, the flux lines are having the tendency to contract in length. To contract in length. So contract in length indicates the attraction between the two charges, right? And this also have the tendency to separate from each other. Separate from each other. And this separation from each other indicates the repulsion between the two charges. The separation between each other indicates the repulsion between the two charges. And next, the electric lines of force are perpendicular to the equipotential surfaces. They are perpendicular to the equipotential surfaces. So this is about the electric field intensity and the electric field lines. If you like my video, like it, share it and subscribe it. Thank you.